Hi, everyone. Gonna go ahead and get started. Good. All right, everyone, welcome to BIOMES. BIOMES is YSE's flagship seminar, bringing you cross-cutting topics in environmental science. My name is Phoebe Ferguson. I'm a second-year Master's of Environmental Science student here, and I'm part of the BIOMES Planning Committee. Today, I am delighted to introduce to you Dr. Angel Xu and Reid Lifset. Further talk, Cracking the Code, the Double-Edged Sword of AI's Environmental Promise. Dr. Angel Xu is an assistant professor of public policy and environment, ecology, and energy program at the University of North Carolina, Chapel Hill, where she is also the founder and director of the Data-Driven Enviro Lab. Angel's research explores the intersection of science and policy and the use of data-driven approaches to understand environmental sustainability. Angel previously held a joint appointment as assistant professor of environmental studies at Yale and U.S. College in Singapore and the Yale School of Forestry and Environmental Studies as an adjunct. She holds a PhD in environmental policy from Yale University and a master's in environmental policy from the University of Cambridge. She's also focused on China and the Global South and has provided expert testimony to the U.S.-China Economic Security and Review Commission. Reid is a research scholar, a founding editor of the Journal of Industrial Ecology, and a resident fellow in industrial ecology at YSE. One objective of industrial ecology is to better understand how to integrate environmental concerns into our economic activity. And Reid's research focuses on the application of industrial ecology to novel problems in research areas. His work explores the evolution of extended producer responsibility, resource and material efficiency, the environmental impact of the digital economy, and circular economy. He's a member of the United Nations International Resource Panel and the Governing Council of the International Society for Industrial Ecology. Reid teaches sessions in industrial ecology and related classes here, and he holds a master's from MIT and master's of MPPM from the Yale School of Environment. Reid and Angel will both share presentations for about 20 minutes, and at the end, we'll have some time for questions. So thank you so much both for joining us today. Angel will start us off.
Thank you so much, Phoebe, for that introduction and for the invitation here. I have so many really fond memories of the School of Environment and also defending my dissertation here. I'm having flashbacks seeing Professor Dan Esty in the back. So don't grill me too hard on this. But let's go ahead and get started. So I'm going to take 20 minutes. I'm just full disclosure, I'm an optimist when it comes to AI. And so I'm going to tell you and make the case for why I think AI can be really transformative in terms of climate change, and particularly in my domain. And then I think Reid is going to give a much more measured approach, probably deservedly, why we should be cautious about AI. And then hopefully we can have some nice interaction. But first, how do we define AI? Artificial intelligence. So I have this definition here from IBM. So it's basically any type of technology that enables computers and machines to simulate human intelligence and problem-solving capabilities. And so from data solving, number crunching, to analysis, to interpreting natural language and human speech, AI is now powering technologies like self-driving cars and chatbots and virtual assistants. But there are many different opinions, wide-ranging opinions about what AI means for society and humanity. From Elon Musk, who talks about how AI is going to eliminate all human jobs, to Sam Altman, the CEO of OpenAI that powers ChatGPT, talking much more optimistically about how AI is going to provide wealth and additional economic opportunity. And then Sapiens author Yuval Noah Harari talks about the end of humanity as we know it because of AI. And then Chaos GPT, which is ChatGPT's evil twin, talks about plotting and trying to dethrone humanity. This year in Davos, I was just speaking with Dan and he reiterated this. So I was excited that I put together this slide because AI was the #1 topic at the World Economic Forum annual meeting of business and government leaders around the world. And so no matter whether or not you're an optimist or a pessimist, a skeptic, or a proponent of AI, I think one thing is really clear is that this is something that is going to be influential in shaping our lives, although we may not know what exactly that looks like. To the point where now even cows can't get away from AI. So now there's an internet of cows where cows are being implanted with IoT sensors so that people can monitor their gut health in real time. And in the climate change domain, we can already see AI being applied to all sorts of climate change domains, from energy optimization to building energy management and efficiency, forest management, also to help us design early warning systems for extreme weather events and better prepare against those, optimizing transport and traffic, grid management, helping us to forecast renewable energy, also in precision agriculture to better apply and minimize pesticide use. And then the combination of smart sensors and satellite data within cities provides a lot of promise for smarter and more resilient cities. So today, I'm going to talk about 3 applications of machine learning or AI in the policy space for climate change. So 3 examples: 1, mitigation, how we can use machine learning to actually predict emissions data from cities to be able to understand their performance against largely voluntary emissions reduction targets. And then secondly, I want to show a case study of how we're using machine learning to model urban heats in urban heat island effect in cities. And then lastly, this is the big elephant in the room. I have a case study on large language models and how we can use machine learning to better evaluate text. So on to the first case study, climate mitigation prediction. Well, as you all know, being at the forestry school in 2015, the Paris Agreement was landmark because for the first time, it recognized the contributions of all levels of government, including cities and regional actors, businesses, and financial institutions to achieving the goals of the Paris Agreement. And this was really a landmark moment because it was the first time that an international climate treaty actually acknowledged the role of these subnational and non-state actors. But when we take a look at the landscape of what cities and what other actors are pledging climate action, this is from one of our databases where we've collated 13,000 cities and regions all across the world that are participating in voluntary climate initiatives, pledging emission reduction targets, for example. So it's pretty exciting, very broad and encompassing, even in the global south. Taking a look at who actually reports data to then measure their emissions reduction targets and whether or not they're making progress on the goals, fewer than 10% of these 13,000 cities actually have any type of emissions inventory data. And this is a really critical gap because for the Paris Agreement, there are these 5-year review cycles, and underpinning these review cycles is data to enforce accountability in this largely bottom-up process. There's not any top-down compliant mechanism in this new post-Paris era. And so we just concluded the first global stocktake in November of 2023. Maybe some of you were at the COP28 in Dubai. And what was really, I think, also surprising for me is that for the global stocktake report, the co-chairs released a synthesis several months prior. And the front page, key finding number 2, talks about the need for credible, accountable, transparent actions by non-party stakeholders to strengthen systems transformation. So this is a report, and the global stocktake was really focused on national governments. But yet they found after a year and a half of consultations that this was a priority for the UNFCCC. So what can be done? Well, I had the pleasure of serving on a 10-expert panel for this National Academy of Sciences synthesis report launched 2 summers ago to take aim at all of the greenhouse gas information data and the methods out there and acknowledging the gaps and thinking about what can be done to address them to make this data more usable for policymakers. And one of the conclusions of this report was that we need more hybrid approaches. We need more non-parametric, non-linear machine learning approaches to hybridize some of the existing top-down and bottom-up approaches to fill in some of these data gaps and to get more granular data for cities, states, and provinces to better manage their emissions. So that's exactly what we did in this 2022 paper. We looked at the European Union for the Covenant of Mayors of Climate and Energy. So they're one of the most active city climate networks, and they produce something like 90% of that 10% of the data that's out there. So we spatialized all of those cities' boundaries, and then we could extract a series of geospatial predictors that correlate with cities' carbon dioxide emissions. So that includes weather variables, how much do they cool and heat their homes and other buildings, fossil fuel emissions from large stationary sources like power plants, air pollution that can act as proxies for transport and mobile emission sources, of course, GDP and population. So we could use all these data and then fit a machine learning model to then predict, even if a city has not produced an emissions inventory, what is that going to look like in terms of their performance? And so here you can see for just 3 cities here, the various underlying spatial predictors. And then this is what the model output looks like. We actually can get annual data points and predictions of what their likely emissions are going to be. And so that's infinitely more useful, because if you look at the triangles, the red triangles, these are the self-reported data, which at best for London, they have 2 inventories. For Tolosa in Spain, they have 2. For the city in Belgium, they only have 1. So you have no idea, are they actually meeting their reduction target, or are they not doing anything on their pledge that they made? And so this is a lot more useful, because then you can draw a line, you can look at the trends and be able to understand whether or not these cities are actually following through on their pledges. And so when we compare the performance, so we went from only having 10% of data to now we can actually predict all of the likely emissions mitigation performance of all of those European cities. On the left, these are the ones participating in the network. And on the right, we can also predict the likely emissions of all of those cities, even if they haven't actually participated in the network. So 74% versus 53%. For the economists in the room, you might be complaining about causality and saying, oh, well, this is not necessarily exogenous, and the cities, they self-select into the network. And you're right. But also what we found is that at least within the cities that participate in the initiative, monitoring and reporting are key indicators of performance. So if they're actually doing the hard work of measuring, developing the inventories, and reporting on their progress, they're much more likely to reduce emissions at a faster rate than just setting a target or even producing a climate action plan. So that means investing in these capacity building support measures to help cities actually develop their inventories might actually be a better predictor of success than some of these other measures. So that's what we found. And now we're taking this model and trying to expand it to other cities all around the world in a global emissions model. So that's the first case study where I'm seeing a lot of potential. Secondly, talking about heat impacts in cities. Again, at the forestry school, you're probably very familiar with this data, which basically shows monthly temperature anomalies from the early 1950s all the way until 2020. And so it's very clear that temperatures are getting, on average, much warmer than they were even a decade ago, with 20 of the 20 hottest years on record just recently. Even this last summer in 2023 was the hottest June, July, August summer period on record. And that caused extreme heat events that broke records in Phoenix and Memphis and Houston. China also 2 summers ago had a record heat wave. They went 70 or more days with temperatures over 120 degrees Fahrenheit. And that's leading directly to deaths in Seattle. It's also disrupting supply chains. So Dijon mustard crises and lack of chili peppers and coffee and wine due to drought and these extended heat waves. If anyone tried to buy a minivan the last couple of years, it was basically impossible because of chip shortages. And I don't know if anyone's a Swiftie in the room, but in Brazil, fans could not attend a Taylor Swift concert because of an unprecedented heat wave that caused a fan to die. So we can see how heat and these rising temperatures are becoming ever more common in cities out throughout the world. But also in cities, we know that heat is not affecting people in the same way. This is a photo from Johnny Miller's Unequal Scenes project. This is in Mexico City. And you can clearly see a much less wealthy neighborhood here on the left, juxtaposed and only separated by a thin roadway to the right, with a much wealthier neighborhood, lush with trees and these amazing sports facilities. And these scenes are common. He has this project all throughout the world, including Los Angeles, where you can see informal settlements here on the roadside, contrasted with these really nice skyscrapers in the background. And if we take a look at this map of Los Angeles on the left, you can see that the neighborhoods that are higher income in green, so I think this darkest green is Santa Monica, has an average per capita income of around 130,000 US dollars, really stands in contrast to these lighter blue neighborhoods that have much less income per person, so around 30,000. And that translates into differences in tree cover, as we found in our urban environment and social inclusion project. So the Santa Monica neighborhood has maybe 70% tree cover, and then the other light blue neighborhoods have only 5% tree cover. And so these patterns are not just isolated to a few case studies. What our research has also shown is that in 97% of cities across the United States with a population greater than 250,000, these are even cities that have not been historically redlined. So these were practices in some cities in the early 1900s that prevented low-income and minority communities from accessing mortgages that would have allowed them to move to more desirable neighborhoods. We actually, even in non-redline cities, we found the same disproportionate exposure pattern where communities of color and people living below the poverty line are exposed to a full degree Celsius higher heat than their wealthier or their white counterparts. And we developed this analysis through using satellite remote sensing. And you can see The method here on the left, essentially the satellites are measuring land surface temperature, so the temperature that's coming off of the ground or from a rooftop or from a treetop. And that has a tendency to, in some ways, in this map in Philadelphia on the left, has a tendency to overestimate the magnitude of this disparity. And when you compare it to another measure like this one on the right, this blue one, you can see this is a measure of mean radiant temperature. So this is about 1 meter spatial resolution. On the left, that's data that's natively 30 meters from Landsat or 1 kilometer from MODIS. So on the right, the lighter blue, you can see that the differences are not as extreme when you get higher resolution data. So that's one of the reasons why we've been experimenting with participatory heat mapping and getting individual scale measurements. And so this, you can see Ian over here who helped us on this study. He actually went and mapped all these routes and for us here on the left. So engaging citizens. So we partnered with the town of Chapel Hill, also Durham County and Raleigh City to send citizens out to collect very high resolution measurements of air temperature and humidity. And then combining that data, so you can see the transects that these poor students walked on a very hot day. And North Carolina is not New Haven, so it was like almost over 100 degrees on that day. We sent them on 2 to 3 mile transects at 2 times in the afternoon, 2 to 3, and then at 5 to 6. And then combining that with remote sensing data on land cover and greenness and built up index on temperature, and also using building structure information from aerial imagery, we trained a machine learning model to then take that map of just a few neighborhoods that we mapped to develop continuous maps of heat of air temperature in red and purple in A, and then in humidity. And then we can combine those two to develop a high resolution, so about 10 meter spatial resolution map of heat stress on the right. And that data is infinitely more useful than having much coarser data from land surface temperature. And so Raleigh, they took that data and they passed a resolution to invest money to coat some of the hottest roadways that were identified in this mapping study with titanium oxide to make it more reflective. And so now we just got a $1.5 million NASA grant to actually develop this work even farther. And so you can see just the differences in spatial resolution between the 10 meter and the 1 meter data. It's much more detail. You can see individual buildings and trees compared to land surface temperature, which is just basically a yellow blob. So really excited about how we can adapt these models and then also apply them to other cities, not just in the US, but around the world. So I'm quickly running out of time. So I will go to my last case, which is on analyzing policy. And so in policy, there's not necessarily always neat quantitative data and spreadsheets to evaluate what's going on. And so there's been a lot of interest in using text as data and leveraging large language models to be able to evaluate trends and patterns. And so you can look into corporate social responsibility reports and policy documents and really gain a lot of insights that don't require you to like manually read every single document, hand code every single one of them, and then try to compare themes. So I'm going to skip through some of the topic modeling, but I'm happy to talk about topic modeling if that's your interest, and just talk about how we're leveraging large language model capabilities. So using machine learning and artificial intelligence to better take aim at net zero accountability. So this is from a project that we are a partner of, which is called the Net Zero Tracker. And we evaluate close to 4,000 companies and governments net zero targets. So do they have an interim target? Are they greenwashing? Or are they using offsets that might be pretty dodgy? And what we found in our analysis is that very few of the cities and the companies that have made net zero pledges to decarbonize, so fully decarbonize their emissions, less than 4% of companies and less than 3% of cities are actually making credible targets. Diving deeper into some of the major companies like Apple and Walmart and Amazon that have made these pledges, only 2, Maersk and H&M, have actually pledged a 90% emission reduction target that's consistent with the net zero definition. That blows my mind. So all these other companies, what are they doing? I mean, they're claiming to be reducing emissions by this big orange bar here on the left, around 2.2 gigatons of CO2 equivalent. But then researchers at the New Climate Institute, they found that what they are actually committing to in that red box is so much smaller, and reading all the footnotes and actually trying to decipher what they're actually doing. So we asked the question, well, now there are all these chatbots in ChatGPT. Let's ask ChatGPT whether or not Walmart's making a credible pledge. And so I asked it, if an entity relies on fossil fuels, is it still pledging net zero credibly? And it was shocking because it says, well, an entity such as a company or government that currently relies on fossil fuels isn't necessarily failing to make a credible net zero pledge. This is shocking because if anyone has read the IPCC report, there is no equivocation. I mean, the number one headline statement is it is unequivocal that humans are influencing climate change. And then also for a net zero future, you can't continue to use fossil fuels. And so this was very troubling to me, also considering that people are now using these chatbots for everything. All my students are using ChatGPT. And so what happens when these chatbots can produce very real sounding responses because we don't know what they're trained on. And they could be trained with a lot of greenwashed inputs from various organizations. So that's exactly what happens when you try to Google net zero. And so we developed Chat Net Zero to try to demystify net zero and to try to develop a credible source. So we've only trained our large language model on scientific documents that our net zero tracker team has verified and the data that we have collected for the net zero tracker. We've developed an anti-hallucination algorithm to make sure it doesn't start to go off the rails and make stuff up. And then also we're developing an anti-greenwashing algorithm. So being able to provide the quantitative metrics that we showed alongside what they're actually claiming to do. And then we provide a source document for everything. So asking Chat Net Zero the same question, it says, no, you cannot continue to use fossil fuels. And it gives a UN report that we had experts vet and to give us the source. So I think there's a lot of potential here. And I see Reid looking at me getting antsy. So I'll just skip through the challenges because you will talk about the challenges and then looking forward to the conversation. So thank you so much.
Hi. So my talk is going to be pretty different. Not so much pessimistic as just a different take on all this. So now that Angel has presented some compelling examples of how AI can advance in environmental research and policy, I'll talk about the other edge of this double-edged sword. I'll start with an overview of the Network for the Digital Economy and the Environment, a project that I co-lead that, as the name implies, examines the environmental impact of digital technologies and digitalization. And then I'll talk briefly about some work in progress investigating the patterns and evolution of research on AI and the environment. Install that. How's that? Better? Hello? Now? Okay, thanks. So the digital economy is growing. I don't think this will surprise anyone, whether you measure it by investment, spending, data transfer, it's growing. And I don't think it'll surprise you to know that the environmental impacts are also growing. This is from a study by the International Energy Agency looking at the energy use of AI, cryptocurrencies, and data centers, showing the growth over this period. One of the things that's interesting about this particular graph is that it doesn't include the period that starts with OpenAI launching ChatGPT. So the generative AI is not included in these numbers. So we know things are growing, both in impact and the spread of digitalization, but the estimates of the impacts diverge pretty widely. This is from a study commissioned by the Network for the Digital Economy that shows these divergences. The estimates for 2015 vary by as much as a factor of 2, and the projections vary by a factor as much as 25. So there's a lot to be done here. Let me put this in another context. To get a sense of scale, if we put the entire footprint of ICT, including the data centers, networks, and devices, on a representation of greenhouse gas emissions for global greenhouse gas emissions for 2022, it would be roughly the size of this red box. That's about 1.4% of global greenhouse gas emissions. And then if we put machine language, the most prominent form of AI, in that, you'll see that it's just a portion of that. But the bigger potential impacts, both positive and negative, and represented by the fuzzy red stuff, are going to come from how we use machine learning and other digital technologies, to what extent their uses will help improve efficiencies and reduce emissions, or whether their uses will actually increase emissions through induced consumption or making fossil fuels more competitive. Even without the new forms of AI, the generative AI, global internet traffic expanded 25-fold since 2010. But interestingly, electricity use climbed more slowly because of improvements in efficiency of data centers and computer chips and software. By the way, ICT includes most of the things that we would all think of as digital, except things related to entertainment like streaming video, television, gaming, and also, importantly, cryptocurrency. Looking at this in a different way, most of the research is being done on the direct effects of technologies and digitalization. That's represented here by the yellow bar, and that's the emissions from both the production, use, and disposal of the equipment. But the research that exists so far suggests that the indirect impacts are going to be much larger, both positive and negative, and we don't really have a grip on what the balance is. By indirect, I mean changes in production and consumption enabled by digitalization. So changes in travel patterns because of telecommuting or because of the use of digitally enabled shared mobility like Uber or Zipcar. So this led to the establishment of the Network for the Digital Economy and the Environment. This is an initiative, collaboration between the Center for Industrial Ecology, University of California, Berkeley, and the Environmental Law Institute. It started modestly in 2018 and has grown. We've raised about $2 billion in foundation grants, and I'm very pleased to say that we just got notification last week that we got another $500,000 grant for the work that we're doing. The premises are that there is a lot of research on the beneficial uses of digital technology, but much, much less on the negative environmental impacts. To give you just one anecdotal indication of this, from literature searches that we've been doing, we found 27,000 papers on AI in the environment, of which a little over 300 were on the negative impacts. So much to do. The goal here is to coalesce a research community and to build a research literature. So we're looking at digital technologies that you'll find familiar. We don't look at all of them. It's not that big an organization. And we do this by, we built a network of researchers and funded external projects. I'll give you some examples. Commissioned papers, built a bibliography, tracked applications of blockchain, funded a special issue, and of course, we're disseminating what we're doing through a website, newsletter, social media, and podcasts. So we have an online open bibliography of close to 1,000 references on the digital economy and the environment. In a rather different vein, we've been tracking environmental applications of blockchain. I think most of you will recognize blockchain because it's a really conspicuous part of the digital technology landscape. Blockchains are decentralized digital ledgers that link records with a cryptographic component that, in a way that can make the records nearly unalterable or immutable, and can avoid the need for a central entity to manage the system. Blockchains are most well known, I think, by all of us as the basis for cryptocurrencies such as Bitcoin. I'm going to talk about that in a minute, but they have many other uses. About 10 years ago, there was a wave of enthusiasm in the environmental community about how blockchain could help improve a variety of forms of environmental management. For example, using chain of custody for resource certification, like the Forest Stewardship Council, or tradable credits in electricity microgrids. But a lot of that was press releases and opinion pieces, and we wanted to see if the reality matched the hype. And so what we've done is tracked actual applications since that period, and we found about 170. We're updating this now, and it's an attempt to, in a sense, do some ground truthing about what's going on with this technology. We built a research coordination network with experts from around the world. The goal here is to get them to collaborate. We provide some funding, provide some discussion platforms and papers, and we've had some interesting outcomes from that. That's done with funding from the US National Science Foundation. So let me give you some examples. This goes back to blockchains. Blockchains are a conspicuous place where there's a divergence of estimates of environmental impact. And it's mostly around what's called crypto mining. This is the step where transactions on the blockchain are verified. And typically these are very energy consuming. The vertical axis up here represents the amount of energy used in crypto mining in a given year. And the estimates range as much as 50 gigawatts in the year. These estimates are important because there's a fierce policy debate going on right now about whether and how crypto mining should be regulated. This work can help. The researchers doing this work examined all the estimates and have come up with a framework for what is a rigorous way to actually make these estimates. Hopefully that will help narrow the divergence in estimates and even identify faulty quantification. A very different project. This is being led by a YSE graduate, Tamar Makov, who got her doctorate here. And this is about quantifying the impact of product returns. So approximately 30 to 40% of products purchased online are returned. Rather stunning statistics compared to only 8 to 10% that are returned from in-person purchases. Needless to say, that adds more activities and more impacts. So Tamara and her team are tracing the actual flows of those product returns through the various stages all the way to their final use. And they have found that for t-shirts and jackets, about 3/4 find a second use. But interestingly, they don't go back to the stores where people originally bought them. They're not restocked. They go to a very wide variety of secondhand markets. And about 1/4 simply never get used and go to some form of end-of-life management. Their preliminary work suggests that the big impact is not in the management of the return process, the trucks that take back those t-shirts and send them on, but rather from the impacts of producing the original good and sending it into the retail system. So let me switch to AI, since this is supposed to be an AI talk. One of the projects of the Network for the Digital Economy and the Environment is an analysis of the focus, extent, and evolution of research on the environmental impact of AI. The OECD just issued a report about this last year and said what you might expect, that we don't know a lot and we don't have a lot of data. And we know that AI is growing rapidly. Like the broader topic of the impact of the digital economy, most of the work on AI is about beneficial uses. And the research on what we informally call bad AI is pretty limited and fragmentary. So most of the focus right now is on the impact of what's called training that Angel already mentioned. Training is the process where a machine language algorithm runs training data to correlate its output against sample data in order to modify and improve the model. This is where all the talk is, and that's because training of AI models requires a lot of computation and thus a lot of energy and greenhouse gas emissions. Until about 2020, there was virtually no attention at all in the computer science community about this. And then there were 2 important papers published, and things are changing. There is more attention. This graph is showing the amount of computation of some major machine learning models as measured in floating point operations per second. As you can see, the dramatic increase on the right in the increase in computation. But it's not all about training, even though that's what all the talk is about. The system for, or the evolution of models starts with obtaining and managing large data flows. And then there's the actual building of the model, the creating of the mathematical model, and then the training as discussed, and then its use out in the real world. There's also a physical component to this. You need computers to do AI. And you run the computers, and then you have to do something with them at end of life. The physical impacts are likely to increase with the increase in the use of AI, but the relative impacts of production are probably also going to increase because there are improvements happening in the efficiency of the use phase in AI. To give you a sense of how this could scale, these are measures of how much energy is used in searches. So you see on the left over here, oops, sorry, pressed the wrong button. Sorry about that. I'm going the wrong way. Such is life. Okay, I'm not going to do that. So Google search is, in this comparison, the lowest. And then if you do a search solely with ChatGPT, this estimate is higher. Bloom is just another large language model similar to ChatGPT. If ChatGPT or a similar AI model is integrated into the searches, you see that the unit impact of a search goes way up. Then when you think about the fact that there are 9 billion Google searches a day, the scaling effect is pretty important. Now, based on what I've learned about this, it's not likely that Google will actually integrate a large language model like ChatGPT into all its searches, but it just gives you a sense of where this inference stage can be really important because of the scaling effect. One researcher has framed the implications this way. He says, a continuation of the current trends in AI capacity and adoption are set to lead NVIDIA, that's a major AI chip manufacturer, to shipping 1.5 million AI servers per year. These servers running at full capacity would consume at least 85 terawatt hours of electricity annually, more than many more small countries per year. Now, this is a framing anecdote. The servers won't operate all the time. There's lots of things built into that. But again, it's to give you a sense of scale. So the analysis that we did, we used bibliometrics, which is a form of analysis to characterize the focus and evolution of literature through quantitative investigation of the pattern of research. You look at article counts, citations, co-citations, and use a variety of content analysis techniques. The first thing we learned is that this is a pain in the rear end. One of the many problems that we confronted is that computer scientists publish most of their papers in conference proceedings, whereas most other disciplines publish their papers in journals. And most bibliometric methods rely on counts derived from journal publications. So right off the bat, the whole thing gets a lot more complicated than is typically the case with bibliometry. But we learned that computer science publications dwarf other disciplines, and as already implied, there's a heavy focus on computational and energy efficiency. There's very little interaction between the work in computer science and the work from other fields. And there is a systematic lack of attention to a whole variety of possible negative environmental impacts. They're just not talked about in the literature. So far, I have found one paper on rebound effects from AI. So the takeaways. The relative and absolute importance of environmental impact of these technologies and of digitalization is likely to grow a lot. And the research is increasing in some places, but a whole lot more is needed. And the research literature is really fragmented. We've got a long way to go to really get our arms around this. So for those of you that are interested, check out the website or our presence on social media. And Angel and I would be really pleased to answer any and all questions. Thanks. Sure, that'll make us seem more sagacious.
Oh, this is heavier than I thought. Okay.
Questions? Come on.
I have one question, and I don't know. Yeah, both of you can see if you can answer this. But I worked in a position where I had to assess these NDC documents and kind of get what they were saying, and the language was extremely complicated, and sometimes they were very badly written. So it was a horrible job. I think that AI could do an amazing thing there by kind of taking out that information really quickly and filling that into a table that then can be, so that all these NDCs can kind of be read in the same structure. But I'm also wondering if it's not going to be used from the other side also, in a way that then the output of text is going to, that countries are going to use AI to write so much more reports that in the end the balance is going to kind of be zero, where you need AI to read those reports. I'm wondering if that's something that has come up.
Yeah, I mean, I guess I can go first. I completely agree with you. So there was no standardized template when they started on the process of the NDCs, the nationally determined contributions. And so that's exactly what happened. There's huge divergence. The paper I didn't get to show you, we did the exact same thing. So we did a unstructured topic modeling to let the algorithms and machine learning discover topics and relationships in the underlying NDCs, and then compare them to what companies and other entities have also pledged. And yeah, I think there is this challenge, I think, and I'd love to hear Reid's take on it as well, where I forgot what the principle or the law, I don't know if it's like Moore's law, where you get like increasing efficiency, and so then you get greater energy consumption as a result of just greater efficiency. So now we don't just have one device, we have 10 devices that can all kind of do the same thing, can help us search the internet or shop or do whatever. And so, I mean, I think that there is definitely a fear, because yeah, these tools now, they make it incredibly easy. You can access a vast number of documents. And so, but yeah, I don't know if I think there still is a lot of hesitation when it comes to, at least within the UN and the UNFCCC, in terms of AI. And they're also considering, they also had a project on blockchain and still trying to figure out exactly what it's going to mean for their countries. But I think that at least on the very basic level, if it could help countries at least benchmark to say, hey, you know, I'm Antigua and I want to know what Bermuda is doing. So then, and then they want to be able to explore their document, and maybe they don't speak, or they're reading a document not in their native language. So then AI can help to translate and then facilitate. And that's exactly what we're trying to do with ChatNet Zero, being able to put the documents, the relevant documents, in a place so you don't get all of the potential noise and all the greenwashing from just huge proliferation of even more information, to really cut down that to that very concrete signal so that you can do that kind of benchmark. And I think that's exactly what's needed, because I think these tools are proliferating. So I mean, even since we launched ChatNet Zero in last September at New York Climate Week, I think now there's like at least 20 other climate related chatbots all claiming to do the same thing. Like there's one that's like Climate Bert Net Zero, which is not a great name. It's based on like the large language model that's named after Sesame Street characters called Bert. I don't know if you have any.
I think there's, you know, if you just read the newspaper, you know that there's an arms race going on between Google, Microsoft, and others to build and deploy these. And there's almost no consideration being given to what their impacts are. It's a heavy duty commercial race. I did some work in a completely different project looking at NDCs, and we found that the information we were looking for on material efficiency versus energy efficiency in NDCs didn't even show up in the indices. It showed up in the national plans, which were hundreds of pages long, and you had to go ferret them out. So this is complicated. But I think the noise factor is going to be huge. It's going to be overwhelming.
Okay. Thank you for the presentation. My question is specifically with regards to the climate mitigation study, where you have many different indicators and you use them to sort of like evaluate how well a city does on their emissions. Like, how do you hold cities accountable to these metrics, rather than preventing them from, say, just like arguing that these like we did not actually release these emissions and these numbers are false? Like, how do you make sure that cities like actually stick by these numbers?
Yeah, that's a really great question, and I think a very real problem. And this is something I experienced when I was a PhD student here at Yale, and I was working on the Environmental Performance Index, where we would release this ranking every 2 years, and then I get a call from Morocco being like, "Where did you get this data? This data is not ours. We didn't approve you using the data." And it's like, well, we're independent researchers. We're collecting data that's available and data that you report to the UN, and so I think there's always going to be these disagreements about the truth of data, and governments, they like to think about their data as being the official source, but you saw how paltry they're doing in terms of actually measuring their emissions and reporting them in a transparent way. And the entire Paris Agreement is predicated on data. I mean, it's all about using data for accountability. So this is a really big topic. In last June, the UNFCCC, they launched a new recognition and accountability framework specifically aimed at non-state and subnational actors. And so it was really interesting because now the UN is getting involved because of this problem. They also want to give this very high level signal that it's really important for these subnational actors to deliver and also to produce data and to be credible in those efforts. And so that's been really interesting. And they should have said something about that and created a synthesis report in Dubai. But guess what? 2 countries were opposed to this new type of framework where you had the UN actually enforcing accountability. Do you have any guesses, Kai, on what those 2 countries would be? Just any guesses? US, yes. And Saudi Arabia. So those are the 2 countries that were opposed. And so now they've delayed it into this quarter because, yeah, US is saying this is violation of country sovereignty. Now UN is trying to tell us how to regulate our cities and also our companies. And so it's creating all types of really interesting governance questions. But I think unless we have like a baseline, like I never say, oh, this data is the truth. It's just one data point that cities can use and factor, because then they can say, if I'm Tolosa, Spain, and I'm looking at another Spanish city and they're reducing emissions faster, according to my data, then they can go and ask, well, what is that city doing? What policies are they adopting that I might be able to transfer to my context? So it's about like being able to also provide this benchmarking and learning opportunity.
Next.
You're
Thank you both. You gave us a good meal. The pizza was also good. But I'm impressed by that, you stayed friends and you were able to take different points of view. Yeah. So I want to ask, Angel, I want to ask you a question, which is, Reid told a pretty disturbing story about how much energy use is increasing and all the side effects, like having to have computers and so forth. Where does that fit into your story? I mean, it's not really a net zero story per se. It's not really about the emissions, but and if we have time, if Reid, you could then get the opposite question.
Yeah, that's a really real concern. And yes, some of your data was really alarming and shocking. And the fact that we still don't know the forecasted energy impacts of generative AI, which now, I mean, yeah, just the bar between the Google search, the energy intensity of the Google search versus ChatGPT, it's alarming. But I mean, I use ChatGPT, I use all of them, almost on a daily basis. And so, yeah, you're constantly iterating and you're not getting a good response. And so then you ask it another way. It's all about prompt engineering. And in the future, I teach a class on data science for our master's program. And I think that is completely changing. I think that just base coding, like learning how to code in Python and R, I think all of that's really going away because the machines can really do it just as well, like if not better. And so it's all about prompt engineering. But I mean, I think I remain still a techno optimist that we're going to have increasing renewable energy penetration and more of the electric grid will be powered by wind and solar. And so I think with these net zero targets and these benchmarks that countries are going to have to meet in order to reach net zero by increasing the amount of green energy. And I think the electric grid, that's like a prime example. And so I'm hoping that even if it does become more energy intensive, at least it'll be powered by green sources. But I think that is definitely a real concern. I also had a project on blockchain. And I think also it goes back to when thinking about different problems or different research questions or different projects, also thinking, okay, well, do I need AI? Do I need to go this really intensive route? And that was the question I kept coming back to in this blockchain project, where we were talking about using blockchain technology as a decentralized ledger to just store climate data. So are there other ways that are less energy intensive that you can think? So I think I think any new technology, it's always so shiny and really attractive. And so it's very easy for us and particularly policymakers. I mean, it's true. Like my brother-in-law, he works for Duke Energy in North Carolina, and he's been there for 20 years. And he said the other day, somebody was like, so what is your plan for AI? And he was like, come on, like, we're not having a plan for AI. Like, not everybody has to be always thinking about and developing this plan for what they're going to do with AI. So I think it goes back to the problem definition. And can you accomplish the same task and achieve the same outcomes just using a different method that's less energy intensive? But I think Reid's right. Like, we have to be much more mindful about how we approach these technologies and not just assuming that because it's the new thing, the next hot thing, that we should all be using AI and these more energy intensive technologies.
So those of you that know me and have ever read Winnie the Pooh know that I've been, my friends call me Eeyore for my pessimism. But you know, the major thing I get out of this is how much we're flying blind. And something I didn't talk about was how hard it is to get good data. You can find things in the literature where individual organizations, Facebook, Google, have published reports. They're not verified by independent entities, but they provide some benchmarks for things. But there's particularly no sense at all of what's going on with inference, with the deployment of AI. I think the rubber is meeting the road here around data centers, because an awful lot of AI is running off of data centers. And the battles there are happening data center by data center. So in ways that are very familiar in the politics of economic development, you know, communities want more employment and taxes, so they're glad to get a data center. And at the same time, it's having a big impact on their local energy generation and also their water use. I'm not sure how it turns out, but I think one thing that we need to do that's going to be very hard is to be very demanding about transparency in this, so we can get our arms around this. That's not a small matter. And if you look at what's happening in crypto mining, as an example, we know that there are all these places around the world, especially in the US and Texas, that are mining Bitcoin and using enormous amounts of electricity. And, you know, we're not really doing anything about it. So thinking about doing something about AI makes me pessimistic. Sorry.
We have time for one more quick question.
Hello. I had a question around communication of data. So especially as you're using AI and these approaches to come up with data, I'm just wondering, like, as a person who is reading this data, are there, for me, am I able to understand properly, like, where that data comes from, and what are the considerations when you're communicating these data and all the algorithms and complexities that go with coming from, like, initially, like, the initial data that you're collecting, which is easy for people to understand, to the final processed information that you're communicating?
No,
Okay.
this one's yours.
This is exactly my last slide, is the black box problem of AI. I think that's a real concern. And as somebody who uses it a lot in my own research, I will say it is often really difficult to understand the decisions that algorithms are making to produce certain outcomes. And so these machine learning models, because they're nonlinear and they're non-parametric, they have a tendency and they're designed to enhance stochasticity. And I think that's also really challenging, because then if you're using like a lot of these, they use like tree decisions. So they say, okay, well, if this happens and I split here and then I do this and do that, it's really hard to really uncover. And so I think that is a real risk. And this is exactly the problem with deep fakes and with Gen AI, is that you might be generating what you think is a real response or is actual data. Now, I've gone onto ChatGPT and it said I've written papers that I haven't written, but the citations sound very convincing. And they know, because of the large language models, all of my co-authors. So then all of a sudden I'm publishing papers with Dan Esty on AI, you know, and it's like, right. But I mean, that's what it's doing. And it's very convincing and really difficult. And so, and that's why in the numbers that we presented on the emissions prediction, I make sure that I have the range of confidence. So we actually use Monte Carlo simulations to then run it over 1,000 times. And then I'm only then reporting the predicted median within a likely range. And then I'm very careful in the communication to say, this is the likely predicted range for a city. So I'm not going to going back to Kai's question, like, I'm not going to tell a city, like, with confidence, like, this is your emissions data for this year. I think that that's like fault. It's even measuring. I used to work at WRI on the GHG protocol, and like, we developed these methods over years to account for greenhouse gas emissions. But I think that that's what's really important. And so only now are governments starting to think about like, what are the governance laws surrounding AI? And like Singapore recently outlawed deepfakes because they could influence elections. So I think a lot of other countries are going to have to think about that as well, and thinking about, okay, what are their requirements? What are the metadata, the data about the data, and the models that you need to actually really transparently interpret what's going on, and then also the end result. And then, as I tell all my data science students, you should be skeptical of any data that you're presented with. And if you don't have any idea about the underlying assumptions and what kinds of parameters were used and what are the coverage and the limitations of the data. And I think that's a big problem. Even in our model, most of the data is coming from the global north. So that introduces huge biases and issues with representation in these models. And we've seen like Amazon have gotten trouble with this, in introducing biases and other types of, like visual camera technology and imaging that also has fallen vastly short because they've been biased in one way or the other. But yeah, that's a really important point, in my opinion.
There's a little bit of work coming out in discipline-based journals about how specific fields need to be careful about the use of machine learning. But it's not about, usually almost never about the environmental impact of that, but rather about the validity of the output of the models in their environmental research. I think it's going to be even harder in the public sphere because there isn't a norm, generally speaking, in the public sphere to wrestle with this. People just want a number and they want to move on.
All right. Thank you so much, Angel and Reid.
Thank you. Thank you, Reid. Can we get a picture?